Alright, live for a little video review from Welch Labs. Um, it is not quite sure where we'll get to this video, but looks for nice candidates to get some learning from the architecture. I know already like another video from another channel reviewing very well how we actually have a model. So I haven't prepared this content, so I don't know. I was looking if there were some link to it here, but I don't even remember the channel. I have an idea of the iconographics used there, but this is how DeppSeek rewrote the transformer.
It was sponsored by KiwiCo.
And it's
More on them
by
later.
KiwiCo. We will get some advertisements, I think, from KiwiCo in here, and you can also maybe sponsor, like get them a thumbs up or help them reach their audience, because they have made, I think, very good work.
In January 2025, the Chinese company DeppSeek shocked the world with the release of R1, a highly competitive language model that requires only a fraction of the compute of other leading models. Perhaps even more shocking is that unlike most of its American counterparts, DeppSeek has publicly released the R1 model weights, inference code, and extensive
So for all the people that thought like that DeppSeek wasn't reliable or not like reliably always, they provided a lot of content through their research, throughout their research. And this is something when I heard about the R1 release, that they made a big boom and it's Chinese products and it's Chinese counterfact, and we still have this bad ideology of like the research made there, but actually it's deeply documented. So let's take a deeper look.
Technical reports, publishing an average of one report per month in 2024, and detailing many of the innovations that dramatically culminated in the release of R1 in early 2025. Back in June of 2024, the DeppSeek team introduced a technique that they call multi-head latent attention. Unlike many DeppSeek innovations that occur at the margins of the stack, multi-head latent attention strikes at the core of the transformer itself. This is the compute architecture that virtually all large language models share. This modification reduces the size of an important bottleneck called the key value cache by a factor of 57. Allowing the model to generate text more than 6 times faster than a traditional transformer in DeppSeek's implementation. But how exactly was the DeppSeek team able to squeeze such a significant improvement out of such a broadly used architecture? Like other modern language models, when you give DeppSeek a prompt, the model generates its response one-word fragment known as a token at a time. Mathematically, this autoregressive approach means that each new token the model generates is a function of all the tokens that came before it. The interactions between tokens in large language models are handled by a mechanism called attention. Attention works by computing matrices called attention patterns. These are the 144 attention patterns computed by the GPT-2 small.
So here is quite simple GPT-2 attention patterns that, let's see.
Model. When given the example input text, the American flag is red, white, and. This model uses 12 separate attention mechanisms, called attention heads, per layer, and has 12 layers, making for 144 total attention patterns. DeppSeek R1 has 128 attention heads per layer, and 61 layers, making for 7,808 total patterns. In both models, the size of the attention pattern is equal to the number of tokens passed into the model. Our example input, the American flag is red, white, and, maps to 9 tokens, so all of our attention patterns are 9 by 9 matrices. Attention patterns are used by attention heads to move information between tokens.
So I think I'm understanding it, but I'm not quite sure I did actually. The explanation is very good. I'm not sure I get it exactly what we're trying to talk about, because the definitions were not really carefully posted beforehand. So if there were more definitions of what is an attention pattern and Where do we got these layers that appears from here, where we had like layers or attention heads per layer, and what is about GPT-2 related in that. I would like understand a little more. And so that, but maybe the exploitation is deeply related to why we do have this key value latents, and why those matters. But here it's not quite like simple to guess. But let's get back to
works in models like GPT-2 and build up a few equations, so we can make sense of how the DeppSeek team made such a powerful improvement. To compute a given attention pattern, we take the input matrix X. This could be the input to any layer of our model, and we'll have one row for each input token, and a number of columns that corresponds to the embedding dimension of the model. This is the length of the vector used to represent each token. GPT-2 Small's embedding dimension is 768, and DeppSeek R1's embedding dimension is 7168. To compute a given attention pattern, we multiply our input matrix X by two separate sets of learned weights, WQ and WK. In GPT-2, these matrices are of dimension 768 by 64, and result.
So now we're getting much more concise information about like what we are actually doing. So we have this notion of embedding words where we transform each word by a vector, and now we actually know what is our pattern. So it comes maybe more easy to understand what we were saying just before.
Attention pattern in the 11th layer has high values, mapping the words flag, red, and white to the output of the final token AND. This attention head has pulled out words in our input that are relevant for predicting the correct next token of blue, which this GPT-2 Small model does correctly predict. Let's dig a bit deeper into exactly how the standard attention mechanism works in models like GPT-2 and build up a few equations, so we can make sense of how the DeppSeek team made such a powerful improvement. To compute a given attention pattern, we take the input matrix X. This could be the input to any layer of our model, and we'll have one row for each input token, and a number of columns that corresponds to the embedding dimension of the model. This is the length of the vector used to represent each token. GPT-2 Small's embedding dimension is 768, and DeppSeek R1's embedding dimension is 7168. To compute a given attention pattern, we multiply our input matrix X by two separate sets of learned weights, WQ and WK. In GPT-2, these matrices are of dimension 768 by 64, and result in two new matrices, Q and K, each of dimension 9 by 64. The rows of our Q matrix are known as queries, and the rows of our K matrix are known as keys. The core idea of attention is that we now search for pairs of tokens that have similar queries and keys, allowing the model to learn various relationships between tokens. For example, a token like flag could query for words that modify its meaning, while words like American can produce keys in certain attention heads that flag them as modifiers. This modifier query and modifier key should produce similar key and query vectors. Mathematically,
Okay, so they introduce something that is semantics. It's like enhanced embeddings somehow.
to find similar keys and queries, we can take the dot product of the keys and queries for each possible pair of our 9 tokens. Similar keys and query vectors will generate high dot products. We can compute all these dot products at once by transposing our key matrix and multiplying by our query matrix, resulting in a new 9 by 9 matrix, where each entry corresponds to the dot product of a single
Well, for 9 token.
key and query. To compute our attention pattern, we apply a masking operation, effectively zeroing out the upper right portion of our matrix. This step is mostly important in training, as it prevents the model from cheating on its task of next token prediction by just looking at the next token. Finally, we normalize our result by dividing by the square root of our embedding dimension and applying a softmax operation, which forces each of the rows of our matrix to add to 1. Now that we've computed our attention pattern, we need to actually use it to process our data. This involves a couple more matrix multiplies. We first compute what's known as a value matrix by multiplying our input by a third weight matrix WV. This computation is identical to the way we computed our keys and query matrices, just with a different set of learned weights. We then multiply our attention pattern matrix by our value matrix. This effectively takes a weighted sum of our values, following our attention pattern. One way to think about this step is as processing our inputs using a neural network, where the weights A are controlled by the data itself. Finally, the attention block in each layer has multiple heads. Each head performs the same computations but with different learned weights, resulting in a different set of queries, keys, attention patterns, and values for each head. The idea here is that various attention heads can specialize in various tasks, like searching for adjectives or searching for other instances of the same token. To compute the final output of the attention block, we stack the results from each head together and multiply by a final learned weight matrix, WO, giving us the final matrix output of our attention block. The attention block is a key part of modern language models, but requires a significant amount of computation. Since the height and width of our attention pattern are equal to the number of input tokens, the number of entries in this matrix scales as the number of input tokens squared. This is potentially a huge computational problem for large models. OpenAI's ChatGPT models now offer maximum context lengths of over 100,000 tokens. For reference, this is about the length of the first Harry Potter book. So computing each attention pattern for ChatGPT's maximum allowed input size is equivalent to arranging the entire text of the book as a single row and column, and then computing dot products for every possible pair of tokens from the entire text. Fortunately, there's a huge computational shortcut that we can take. As large language models generate new text, a single token at a time, the attention patterns themselves don't actually change that much.
Well, I must say that this video is pretty good so far. It's just that it's not for me right now. And I kind of like it, but at the same time, I know that I don't have enough knowledge, and I'm being like bullshitted like a lot of information around. There is a lot of notions I don't have, and even if I thought the first that I will be given enough of the materials that being reviewed in the article papers and the scientific papers, I don't have this information here. So I'm not sure that I want to continue with this. But anyways, it was kind of nice for what we have seen. A bit too technical. I don't have the background for it. The most replayed portion is just before the KiwiCo sponsoring. So maybe I will jump there. Well, all of this portion here is not really viewed. Number of entries in cache. This is the optimization somehow. This is the one that has it less. And
KV caches are not a new problem. One popular solution is to reuse key and value matrices across multiple attention heads. In multi-query attention blocks, instead of having unique key and value matrices for each attention head, we share a single key and value matrix across all heads. This reduces the required size of our KV cache by a significant factor of the number of heads per layer, 128 for the DeppSeek R1 architecture. However, this modification does
and by the way, if we have a look at Olema, I don't know if DeppSeek R1. There's also DeppSeek Coder. I don't know how long ago this was. Oh, there's a 236 billion model. Interesting. It's 133 gigabytes. I really have to clean my computer. Alright. Code language expert that achieves performance comparable to GPT-4 Turbo. Which is not really. There's a release and it's 5 gigabytes for the 8 billions. And if we compare to OpenAI 01 1217, Code Forces, GPQA Diamond, Math 500, MMLU, and all of them, and DeppSeek R1, they don't precise how much parameters they are using here. They don't say anything about the number of parameters. All right. So this is it for this open door. And I guess I have to say thank you for this video review. I don't think it's something I will do a lot because I get very quickly impatient. I prefer to create content than to review some content that's already available. It's just a way to create publicity for the content that has been created. And of course, it's only for educational purposes. Alright, thank you again for watching the stream.